We're going to continue on now with Chapter 2 and deal with scientific notation. This expresses any number as a number between 1 and 10, which is known as a coefficient. Multiplied by 10 raised to a power, which is known as an exponent. So the basic concept is we find a number between 1 and 10, and that is where we put our decimal. So the number between 1 and 10 is 4.6. Then we multiply it by 10 raised to how many places we had to move the decimal. So 3, 6, 9, 12, 15, 18, 21, 22, 23. So this is 4.6 times 10 to the 23. If you have a number less than 1, it's the same concept. We find the number between 1 and 10. In this case, it would be 2. We multiply it by 10, and then how many places we move the 0. 3, 6, 9, 12, 15, 18, 21, 22, 23. But to show that it's a number less than 1, we use a negative 23. On the next page, we have dimensional analysis, and we are going to forget about that for now, so we don't have to learn it yet. And then on the next page, we have accuracy versus precision. Accuracy is how close a measured value is to the actual answer. Precision is how close a series of measurements are to one another. So if we look at the 4 targets, we see in the first one an accurate attempt. The arrow ended up in the bullseye. There's no precision because there was only one shot. In the next one, we have 3 arrows that were shot. They are all close to one another, so they are precise. But it's not very accurate because it missed the target. Here we have 3 arrows that hit the target. So it is precise because the 3 arrows are close together, and it's accurate because they all hit the target. And finally, here we have 3 arrows that are neither precise nor accurate. So in the chemistry classroom, this would be seen more with a measurement. So if a measured mass equals the following values: 2.63 grams, 2.63 grams, 2.62 grams, which is still pretty close, 2.63 grams, and 2.62 grams. Now, if the actual mass and actual mass equals 2.63 grams, then the measurements were precise because they are all close together, and the measurements are accurate because they are close to the actual answer. But what if the actual mass is equal to 3.79 grams? Well, in this case, the measurements that you made are still precise because they're close to each other, but they are not accurate because they are not close to the actual answer. And the last thing we're going to cover today on the next page is percent error. Error is the difference between a value and the actual or accepted value. Percent error is the difference divided by the accepted times 100. The times 100 just makes it a percent. So a student measures the mass of a piece of silicon as 2.34 grams. The actual mass is 2.01 grams. What is their percent error? So we do ESA for the class, equation, substitution, answer. So percent error is equal to difference between the two values over the accepted times 100. So percent error is equal to the difference between 2.34 and 2.01 is 0.33 over the actual or the accepted value 2.01 times 100. So on a calculator you should do the work, but percent error is equal to 16.4%. So that takes care of the notes. I have a quick video to show you on scientific notation, and then that will be it for today.
In order to write these numbers in scientific notation, they need to be in the form of A times 10 raised to the power of B, where A, called the significand or mantissa, is greater than or equal to 1 and less than 10. So to rewrite 15,600,000 in scientific notation, we first need to determine where we'd have to place the decimal in order for A to satisfy this condition. Right now the decimal point is here, and in order to satisfy this condition for A, the decimal point would have to be placed here. Now by counting the number of decimal places from here to here, we can determine the exponent on 10. So we have to move it 1, 2, 3, 4, 5, 6, 7 places to the left in order to satisfy the requirement for the value of A. Therefore, written in scientific notation, we would have 1.56 times 10 to, we move the decimal place 7 places to the left, so our exponent will be positive 7. Now sometimes it's difficult to remember whether this exponent should be positive or negative, and here's an easy way to remember. If we start with a large number, like we did here, 15,600,000, in order for this to equal a large number, this exponent here will have to be positive. Multiplying by a positive power of 10 will make 1.56 larger. Now let's convert a small number to scientific notation. Again, the first step is to determine where the decimal point would have to be in order to satisfy this condition here for A. So the decimal point would have to move from here all the way to here to make 8.72. Now let's count how many decimal places we have to move from here to here. It would be 1, 2, 3, 4, 5. Which means in scientific notation, this would be equal to 8.72 times 10 to the, because we move the decimal to the right, it's going to be negative 5. Again, to me, moving right and left gets confusing as to whether the exponent should be positive or negative. If you can just remember that the original number was very small, then multiplying 8.72 by a negative power of 10 is going to make a very small number like we started with.